Welcome to Revolution Against Evolution. I'm your host, Doug Sharp.
Your co-host, Rich Gear, here with you, and we have a special guest that I am very honored to speak with, Dr. Raymond Damadian, and so glad to meet you and be able to talk to you face-to-face like this. And
yeah, so we're very, very pleased to be here. We're in the Phonar Corporation in New York on Long Island, and we traveled here just today to meet with Dr. Damadian and take a look at his special discoveries that he's made and learn about the MRI system that he was instrumental in inventing, developing, and making it the successsul procedure that it is today.
It's an amazing thing. So, yeah, I guess I hardly know, except maybe to start at the beginning. Doug, you had a question way back in the back in the day when you started going into this kind of stuff.
Well, there was an experiment that you did back in the day called the choleric catastrophe.
Yes.
And that had something to do with your discovery that led you to think that this was a possibility.
I think that the way I can begin describing this, Doug, is I was dedicated as a university faculty member to doing research, scientific research, and I enjoyed doing scientific research, and I wanted that research to be of some value, of some significance. And the one area that caught my interest in the line of research was this curiosity that the human body is a walking Con Ed plant, generating electricity as you walk around.
Yeah.
And when life comes to an end, the Con Ed plant shuts down. So, what is that Con Ed plant? How do we generate voltages inside our body, allow us to move my body, allow our brains to think, allow us to move our legs, and so on and so forth? So as I began wondering about that, the first piece of the puzzle was if you looked carefully at a living cell, you saw that the living cell itself generated a voltage. So every living cell in your body generates a voltage. And that's how you become a Con Ed plant, a walking Con Ed plant. So how does that cell, like a battery, that living cell, how does it generate that voltage? And there were two scientists in Britain who got the first step. The two scientists were Hodgkin and Huxley. And they said that if you look carefully at the chemistry of that living cell, you saw a sizable amount of the atom potassium on the inside of the cell. But that atom was not a neutral atom, it carried a 1+ charge. And if you measured it, you got 140 of those potassium 1+s inside the cell and only 4 on the outside.
Oh, yeah.
So now, if you took those same numbers and put them into a battery equation, you calculate the voltage that you get in the living cell. You get a voltage across that cell of minus 90 millivolts. So that's where it's coming from. It was coming from the asymmetric distribution of the large amount of potassium 1+ charge inside the cell and a small amount on the outside, 140 inside, 4 on the outside.
And so you were using a methodology that I remember from my chemistry days called nuclear magnetic resonance spectroscopy, and that was a process that measured these electric voltages that you're talking about in samples.
Well, I didn't get there yet, so I have to go through another step. So.
Because I'm recalling I read your book and I was talking about they're looking, or the postulate was there was a sodium pump or something.
No, okay, that's the step I need.
That's the way you want to go
Yeah.
to. Okay,
That's
good.
right.
All right, we're not getting ahead of
That's
ourselves.
the step I need.
Good. Okay. All right.
So you had 140 potassium inside and you had 4 outside. But on the outside of the cell, you had another atom with a 1+ charge that was sodium. And you had 140 sodium outside and 4 sodium inside. So as soon as the scientists saw that, they said, well, how does the living cell do that? how does it selectively accumulate potassium and kick sodium out? So the scientists in Britain that studied that said, it must have a sodium pump.
Okay.
There must be a protein sitting on the surface of the cell, and it pumps potassium in and it pumps sodium out. The sodium pump. Now, I was doing my research in kidney at Washington University in St. Louis, and Dr. Bricker was my professor at the time, and he said, he was explaining the pump. And I said, well, Dr. Bricker, I said, has anybody ever isolated the sodium pump? And he says, the guy who does that's going to win the Nobel Prize.
Oh boy.
So now that got my interest. So I said, all right, I got to go find that sodium pump. I got to try to write it down. And with my interest, I got interviewed by the Professor R.A.K. Solomon, who was professor of biophysics at Harvard. And he was interested in I come and do research there. So he says, Damadian, what research you want to do? And I said, well, Dr. Solomon, I'd like to isolate this sodium pump. Damadian came to the right lab. What do you mean, Dr. Solomon? He said, well, we're already working in that direction. I said, what do you mean? He said, well, my thought on the way to do this, Damadian, is to do the experiments on bacteria, the E. coli bacteria.
Oh, okay.
And then we'll try to make a mutant, Damadian, of that E. coli bacteria that can't accumulate potassium. And then we'll have two bacteria. We'll have the bacteria that can do it, and we'll have the same bacteria that's a mutant that can't do it. And now, if we go ahead and fractionate the proteins, because everybody says the pump is a protein, and we fractionate the proteins of both of them and compare the proteins, we should find the one that doesn't match up. And the one that doesn't match up, that's your pump,
That's your pump.
Damadian.
Okay.
I said, oh, well, that sounds like a good idea, Dr. Solomon. I said, but, this pump is so central to life itself, and the central to generating living electricity. How do I know that I'm going to be able to even find such a pump? Because the bug that I want to be missing the pump has to be alive in order for me to isolate it. So
Yeah,
what
that was
about
kinda
that?
catch-22.
And Dr. Solomon said, that's your problem, Damadian. Anyway, so I then started my research to make this mutant. And within about 3 months, I got the mutant. And I got a mutant that couldn't normally accumulate potassium. So now I'm ready to start fractionating the proteins and find the one that doesn't match up. So I do it for about 3-4 months at Harvard, and then I got drafted into the Air Force, and then my colonel that was my commanding officer liked the research that I had been talking about. He says, okay, man, you can keep doing that work while you're at the School of Aerospace Medicine, as long as you add the rocket fuel to your test tubes every so often. Because that's the one we're committed to look at, Damadian, called hydrazine. I said, oh, Colonel Bitter, I can do that. I said, okay. So go ahead, Damadian, look for your pump. So I went ahead and I fractionated the proteins. For another 2 years, I'm looking for this pump and doing electrophoresis and comparing, and I'm not finding anything. So then I got hired to be a professor at the SUNY, State University of New York, Downstate Medical Center, a big medical school. And I went and I continued my research. And I'm in the biophysics department, I'm in the internal medicine department, another 6 months. So after about 6 months of comparing this mutant to the parent strain, I'm still not finding. So wait a minute, Damadian, one thing you ought to do, you should go to the scientific literature and see how strong is the evidence for the existence of this pump. Because if the evidence is not solid, and it's not really strong evidence, and it doesn't exist, Damadian, you'll be looking for it for the rest of your life, and they'll find it if it doesn't exist. So go check out the evidence that tells you how strong the evidence is that there is a pump that does exist. So I went to the library, intent on spending several months there to check out the validity of the evidence that there was a pump and it did exist. And I'm not there more than a few weeks, and I run into a book by a professor at the University of Pennsylvania named Gilbert Ning Ling, L-I-N-G. 500-page book entitled The Association Induction Hypothesis, in which he says flatly there is no pump. That the evidence for the pump is fiction.
When was it? How was this a contemporary book at the time?
Yeah, it was a
pretty recent?
contemporary book at that time.
Okay, yeah, all right.
And it was called A Physical Theory of the Living State, and the professor was Gilbert Ning Ling, L-I-N-G, okay? So then I said, well, now he says there's no, it provides 500 pages of proof that there's no evidence for the pump. So, and it was just a conjecture on the British professors anyway. They hadn't provided evidence for it. So then I started looking at it in more detail to see what was going on. And then the other question that came up was, if there is a pump, does the cell have enough energy to run this pump? Because the difference between the inside and the outside was large, and it was going to take a lot of energy. So then I went ahead and did experiments with Dr. Larry Minkoff at the time, and we did the experiments to measure the amount of energy that the cell could generate through metabolism to run this pump. And it didn't even come out close. The amount of energy that the cell could generate from metabolism was 14% of the calculated energy it would have to have in order to run it. And we published a paper entitled The Caloric Catastrophe.
And so, how did this set you off into the search for that resulted in the MRI?
Well, we started publishing that, okay? And we published first the caloric catastrophe, Larry Minkoff and I, and then we also published some other papers where I had come to the conclusion that the evidence for the pump was not very strong, and I suggested an alternative hypothesis that was similar to what Professor Ling had proposed, and namely that this atom's got a charge. It's got a 1+ charge. So maybe it's accumulating just by sticking to the negative atoms that the cell is composed of, because the cell is loaded with negative atoms. And those are negatively charged atoms that part of the nucleic acids, they have phosphates that are negative. The proteins have carboxylate groups, they carry a negative charge. So the potassium's just sticking there. And that's how you get a big concentration. But there was a prevailing question that I had. Once you came up with that and you got rid of the pump, because the pump was doing, although the pump was fiction, the fiction was doing this that I now had to do without this fictional pump to do it. and what I had to do was account for why potassium and not sodium. Because they're both 1+ charge and they would both stick. So how come the cell was able to accumulate potassium and exclude sodium? How did it do that? And that's what the pump was providing, and we threw out the pump. And that was more difficult, all right? So in the course of doing this research, I started looking at all kinds of literature on this phenomenon. And the phenomenon was called the ion exchange phenomenon, because the cell was exchanging these atoms. And these atoms that carried a 1+ charge are referred to as ions, I-O-N-S. So we were really doing research on the potassium ion inside the cell and the sodium ion outside the cell. And that was ion exchange.
Isn't there a chromatography that's based upon that? The chromatography that works with
okay. I was
We're not there yet.
I was coming to that. All right. So then I said, well, look, if there's no pump, because we had done the evidence to show that there was not enough to run it, how does the cell make the choice? How does it carry out this necessary ion exchange? And so I said, well, wait a minute. There's a whole industry of ion exchange. The chemists make these things called ion exchange resins. They're little sulfonated beads, and you take them and you pour them into a glass column.
Okay.
And you take a solution that has 10 molecules, where they're all different molecules and you would like to separate them. You take the solution with the 10 molecules, you pour it in the top of the column, it comes percolating down through the column, and you collectively successfully make test tubes, and each test tube has different materials in it, and you separate the 10 molecules. And that process is referred to by the chemists as chromatography.
Okay.
All right?
I
So
remember
this-
doing that in my chemistry.
You remember that? Okay.
So this, and the things that are doing the job for you are these little beads called ion exchange resins. And as I was doing research, I discovered that these ion exchange resins were able to make the same choice between sodium and potassium that the little cell was making.
Oh, okay.
No, wait a minute. The chemists don't have a pump to explain the bead. How do they say it's choosing potassium over sodium in their beads?
Right.
Now, the beads didn't choose it to the same magnitude of difference as the living cell, but they chose it. They have a 2-to-1 or a 3-to-1. How does a chemist explain how that happens? All right, they're looking. Sorry. Well, right off they said it was simple from their perspective. Number one, the ion was sticking to the negative charge inside the bead. But more importantly, it was tight space inside the bead.
Mm-hmm.
And it could only accommodate so much water. And these atoms, these ions, sodium, potassium, they don't run around in life naked.
Mm-hmm.
They have surrounding on the outside a covering of water, what we refer to as the water atmosphere. And that's the way they live. They don't live naked. They have an atmosphere of water. And what the chemists said to explain how the beads were choosing potassium over sodium, said, wait a minute. The hydrated potassium, the hydrated sodium with the water around it is bigger than the hydrated potassium.
Okay. Okay.
But specifically, you might ask, why?
Yeah.
And the answer is that the potassium atom is bigger than the sodium atom. The sodium atom is smaller. The net result is that the surface area of the sodium ion is smaller in square centimeters than the surface area of the big potassium ion. But they both have the same charge. So the charge per square centimeter is going to be greater on the 1 plus sodium than the charge per square centimeter is going to be on the 1 plus potassium.
Okay, so what does that mean?
Well, then that means that the density of charge is greater on the sodium ion than the density of that same 1 plus charge is on the potassium atom.
Okay.
All right, well, the result will be that because the density is greater on the sodium atom, it's going to attract more water molecules.
Okay.
And you won't right off know why, but the answer is that the water molecule is what we refer to as a dipole.
Mm-hmm.
That is, it has one end of it is negative, and the other end of it is positive. So if you've got a positive potassium, that water dipole will stick to it with the negative end. And that's how it puts this sphere of water on around the outside of it. Now, so when you look at it carefully then, the fully hydrated sodium ion is bigger than the fully hydrated potassium ion.
Okay. All right.
And the long and short of it is it takes up more space.
Oh, that makes more
And
sense.
if it's tight space, it's going to pick the hydrated potassium ion over the hydrated sodium ion.
So that's the reason why it does that. Okay. Now.
All right.
Okay.
But now once it's able to do that, it generates a voltage. Because you got 140 potassiums inside the cell and you only have 4 outside. And that's where your electricity comes from.
Okay.
And so you are then in the getting to the MRI story, which already we're running close to being
We're gonna
out
keep
there.
going. This is too interesting. I'm learning a lot of stuff here. You know.
But I'll get there. You got to be patient.
You gotta- you gotta do this. Audience, we'll get there. It's
All right.
it's worth
No,
the story. Trust me.
I'm going there right now.
Okay, we're going there now.
So I'm publishing this, that forget the pump, everybody. The evidence for the pump is not strong, but the way this is happening is the way Dr. Ling says, that the hydrated potassium is sticking to the negative charges on the inside of the cell, and the cell is able to choose potassium over sodium because the hydrated potassium is smaller than the hydrated sodium. So all of a sudden, I get a phone call from Dr. Freeman Thorndike Cope, who was a scientist, MD, biophysicist at the Naval Air Development Center in Pennsylvania, in Doylestown, Pennsylvania. He says, Damadian, I've been reading your papers. Yeah, so? Well, how'd you like to prove what you're saying, Damadian? I said, what are you talking about, Cope? He says, listen, I think I know how to prove what you're saying, Damadian. What are you talking about, Cope? He says, look, he said, if you're right, and it's because of the attachment that it's being accumulated, not because of the pump, but because that ion is attaching to negative charges on the inside of the cell, we should be able to prove that by doing NMR. We can do the NMR of the potassium atom and collect the signal from the potassium atom.
Okay.
And if you're right, Damadian, if the potassium atom is coming in by sticking to the negative charges, Damadian, it's going to change that signal. Because if it's in loose water, Damadian, and we look at that signal is going to take longer to decay than if we look at the signal of the same atom that's bound. So if you're right, Damadian, that signal should be a longer lasting signal in the potassium, in the potassium atom. When it's attached to the negative charge on the inside of the cell, that should shorten the decay time. And if it's not attached, it won't have any impact on the decay time of that signal.
Oh.
Now, maybe what I should do is just try to give an idea of this signal that I'm talking about.
Okay,
What we're talking about is this technology we call NMR, nuclear magnetic resonance. Then when we started to use it, it got renamed as MRI. But NMR equals MRI. And the reason there was the name change is when we first introduced this technology to the medical community, they wanted the nucleus, the N, to go away because it suggested radioactivity.
Right.
Right, yeah.
And when we started using it, the radiologist wanted to add the letter I to make it an imaging technology. So NMR, nuclear magnetic resonance, changed its name to MRI, magnetic resonance imaging. But NMR equals MRI. They're the same thing.
So magnetic resonance has been around for a while when you started looking at, but in real small, is that?
No, it's a laboratory procedure that they used it for.
Yeah.
No, but you're asking a good question, okay?
Yeah.
And it all goes back to the early discoveries by people, famous physicists like Isidore Rabi and others. And what they were able to show that if you took these atoms and put them in a magnetic field, and from theory they anticipated that, and then if you fed a radio signal into the atom and then shut it off, the atom would answer back with its own radio signal.
Wow. How far back is that?
So
And that was the
does it
first set
stimulate
of experiments in 1929.
1929, okay.
Does it actually stimulate the atom to do that? Is that what you're saying? Does it stimulate the atom?
Yeah, that's right. You're putting a radio signal to stimulate the atom. But I should be more specific. That radio signal is going into the nucleus of the atom. And it's the nucleus that's answering back with a radio signal.
So that's what you use to identify, based upon that signal, that's what you use to identify the chemistry that's coming back.
Exactly. Now, what Dr. Sharp is describing is that when we get this broadcast from the atom, the broadcast allows us to determine the chemistry of what that atom is doing, who it's bonded to, how many different kinds of molecules with the same atom are in it. And that ability to get a radio broadcast from the atom allows us to do a chemical analysis of the sample without ever touching it. I can do a chemical analysis of a sample just with an antenna around the outside. I don't have to go in and do a detailed chemical analysis.
This got you thinking, though, right?
Huh?
This got you thinking when you saw this.
Right. Dr. Cope calls me up, says, let's look at your theory, Damadian. So I said, Cope, so what do you want to do? He said, well, I know of a small company on the outskirts of Pittsburgh called NMR Specialties, and they have this technology, but they have a special kind of NMR machine. The present NMR machine that everybody's using, Damadian, does chemistry and does spectroscopy. So what you end up, what the chemist does is he takes this test tube, puts it on the inside of the magnet, and then he looks at the frequencies of the different atoms that are inside the test tube, and then he maps it, and that's a spectra. Mm-hmm. I'm suggesting something completely different, Damadian. We won't look at the frequencies. We will look at the signal itself and see how long that signal lasts.
Okay.
And if you're right, Damadian, and if your argument that the potassium is accumulating by sticking the negative ions, that should affect the decay time of that signal. That should affect the relaxation time of that signal, which is another name for the decay time. Mm-hmm. If you're right, Damadian. We'll measure the decay time of the signal from potassium in liquid water, and we'll measure the decay time, the same decay time, of the potassium when it's inside some tissue. And if you're right, Damadian, that decay time should change markedly. If you're right, Damadian. And the way we can prove it is we just put it in this special NMR that allows us to measure the decay time of that atomic broadcast. Okay, it sounds good, Cope. What do you want to do? He says, well, right away. He says, oh, okay. And he says, I got a lab in New Kensington, Pennsylvania that will do it. We'll cooperate with us. Same place I bought my machine, but it allows us to measure the decay time. It's not good. All right, so I said, all right, let's go. Let's set up to do it, Cope. So Cope says, okay, Damadian, takes the tote, takes this test tube with the halobacter with 20 times the normal potassium, puts it inside the magnet with a coil around it, and instantly measures the potassium and measures decay time and shows that the decay time is much shorter. I said, Cope, I can't believe what you just did. I said, what are you talking about, Damadian? I said, listen, Cope, I've been measuring this potassium for several years, and I have to go through an elaborate wet chemical analysis method, and if I don't drop the test tube, and here I give it to you in a matter of 3 seconds with non-invasive electronics, you make the same measurement that it takes me days to do. I said, Cope, I can't believe what you just did. I said, Cope, do you realize that if we could ever do that on the live human body, we would be able to go from one tissue to the next and get its chemistry without ever invading anything? No, because here I am talking about a magnet that's 2 1/4 inches in diameter, and I'm dreaming about putting a human body in there, which was going to be absurd. So I says, oh, Cope, Cope says to the man, he says, I don't even know where you would start. I said, well, I got an idea on that one, Cope. What are you talking about? I'll do it on cancer, Cope. What's in your mind? I said, well, from everything I've read on the iron composition of cancer tissue, I know that the iron content and the iron composition of cancer tissue is abnormal.
Okay.
And if it's abnormal, the signal ought to be abnormal. And we should do it on the water signal, because I'm expecting that the potassium and sodium is going to be abnormal, so the water signal should be abnormal, and we should get an abnormal water NMR signal from cancer tissue as compared to healthy tissue.